Okay, good morning. Shall we start? I've already started the recording.
Yes, sir, we can start.
Yes. Okay. Yeah. So, um, have you people revised something about specific heat, something about latent heat of vaporization? Let me just uh, let me just start by revising some of these concepts. So, if I say that, let me start writing. If I say that we specific heat of water, right? Now that we know that water exists in different states and we have to work with different states. So let's say water in the liquid form has a specific heat of 1 kilocalories per kg Kelvin. What does that mean? Anybody can explain what does that mean?
Sir, it will take 1 kilocalorie to raise the temperature by 1 Kelvin for 1 kg of water.
Right. So if I take 1 kg of water, I want to heat through 1 Kelvin, let's say from 330 Kelvin to 331 Kelvin, or 4 or 290 Kelvin to 291 Kelvin. The amount of energy required is 1 kilocalorie, right? Or if I cool, let's say 1 kg of water, we cool through 1 Kelvin. So we want to cool, let's say, from 338 Kelvin to 337 Kelvin, or we want to cool from 300 Kelvin to 299 Kelvin. Amount of energy or heat, we are using the words energy and heat interchangeably. So I think we will continue using one word. Heat to be removed from water would be 1 kilocalorie, right? That's the meaning of the word specific heat. And it is an intensive property in the sense that it does not depend on matter, because we are amount of matter, because we are writing per unit mass, right? So for example, if I take 5 kgs of water and I want to heat through 1 Kelvin, the energy required would simply be 5 kilocalories. Or if I want to cool 4 kgs of water by 1 Kelvin, the amount of heat to be removed would be 4 Kelvin, right? And we are writing per unit Kelvin, that means for 1 Kelvin change, so 1 Kelvin change, the amount of heat required for this 5 kg is 5 kilocalories. But if I want to heat up through 10 Kelvin, so for example, it becomes from 330 Kelvin to 340 Kelvin, 10 Kelvin, it would just be 10 times this number, right? It would be 50 kilocalories, right? So that's why we use a specific heat. Same way, if I want to cool from 338 to 318 Kelvin, now it's a change of 20 Kelvin, okay? Then I would require 20 times as much heat to be removed. So I would need to remove 80 kilocalories, right? So that's the importance of specific heat. But sometimes, let's say, when we are talking about um, okay, another point is we could either write specific in terms of, so CP, specific heat, would have units of kilocalories per kg per Kelvin, right? So remember what this is. This is the amount of energy required, the amount of heat required. So you could have any heat units. You could have joules, you could have kilojoules, you could have calories, you could have kilocalories, you could have kilowatt hours, right? You could have any set of heat units. It is per unit mass or per unit mole. So it is mass, right? So mass, you could have units in terms of mass, in terms of kgs, in terms of grams, in terms of pounds, right? Or you could have units in terms of mass, not represented as mass amount in kilograms, but mass represented in terms of the amount of moles. So you could have gram moles, you could have kilomoles, you could have pound moles, right? Sometimes we represent this denominator to make it into an intensive property. That means to make it independent of the amount that we take. Sometimes we write in terms of volume as well, right? So you could have volume of the substance being represented in terms of meter cube, in terms of liters, in terms of ml, whatever, right? Whatever set of volume units that you like. This becomes especially important because if we are talking about substances like gases, then it is much easier to measure the volume of the gas. So you could measure the specific heat of a gas, let's say air specific heat. You could say that the air specific heat is so many kilocalories per meter cube. Now that per meter cube may be referring to at STP conditions, per Kelvin change. But that's not, we don't write this very commonly, but yes, sometimes you will see that it is represented per unit volume as well, right? Not very often, we won't do that many times, but very rarely you will find sometimes specific heat represented in terms of volumes. Okay, you could, the denominator Kelvin is a per unit change in temperature, right? And then you can use any of your favorite units for writing the per unit change of temperature. So you could write in terms of Kelvin, you could write in terms of degrees centigrade, you could write in terms of degrees Fahrenheit, you could write in terms of Rankine. Anyway, Rankine we should not write, okay? But we could write in terms of degrees centigrade or degrees Kelvin, or per Kelvin change or per degree centigrade change, right? So your CP units, you could have various units. So one could be, let's say, kilocalories per kg Kelvin, or you could have calories per gram mole per degree centigrade change, or you could have calories per gram mole per degree Fahrenheit change in temperature. You could write in terms of joules per gram mole per Kelvin change, or any combination of the units of energy, units of mass or moles, and units of temperature. And we have seen in our first class how do we convert units from one set of units to another set of units. So you should be able to convert units from one set of units to another set of units.
Uh, so
Yeah,
could you please explain the volume part again? Like,
yeah. So if we are talking sometimes about gases, so rather than, so if I take a gas that is getting heated from, let's say, 30 degrees centigrade to 200 degrees centigrade, uh, we would rather we could rather talk in terms of per unit volume of gas. So we don't write CP. Suppose CP I want to write, CP is suppose 7 calories per gram mole Kelvin change. So let's say CP of air. So rather than writing in terms of gram moles, I could write in terms of per unit volume of 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 that gas. But then the only problem with volume is we have to be careful that volume is going to change with temperature and pressure. So we have to be sure in terms of what volume we want to write. So we could write in terms of per unit volume measured at STP. In a sense, it is writing in terms of gram moles only, because one 1 meter cube at STP, we know it corresponds to so many gram moles or so many
Like for a
moles.
closed system, it is an indirect representation of the moles only.
Yeah, it is a representation of moles only. So it is just sometimes just becomes convenient to write, but we will not be writing that. We will abundantly take precaution that we don't write this. Only in some books you may find specific heat written in terms of per unit volume. But so we will not write that, because we will write in terms of units that don't change with temperature. So suppose if I take 1 kilogram of air, whether I measure that 1 kilogram at 30 degrees centigrade or I measure that 1 kilogram at 0 degrees centigrade, that 1 kilogram is going to be 1 kilogram. Volume will change if I measure at 30 degrees centigrade or 0 degrees centigrade. So we will write in terms of units which are not changing with respect to the conditions that we are going to talk about. So volume, just I mentioned in a passing, just so that in some books you may find these weird set of units for volume. Okay, shall we go ahead? So if you think in terms of heat, right, if you want to plot heat, suppose I want to plot a graph now of heat, or I could write enthalpy, right? I'm just a different way of saying, if I want to write enthalpy versus temperature in the form of a graph. Okay, let's say for 1 kg water. Okay, I'm drawing this graph for 1 kg of water. Okay, suppose I increase from if I want to increase the temperature from 330 Kelvin to 340 Kelvin. Okay, in temperature I'm writing in terms of Kelvin. So how much energy would be required? How much enthalpy would be required for 1 kg of water heating through 10 degrees centigrade? Suppose I want to heat from 330 Kelvin to 340 Kelvin. The amount of enthalpy required would be M mass into Cp, 1 into change of temperature. So that is 10. So mass I have written in terms of kgs. Cp I have written in terms of kilocalories per kg Kelvin, and 10 degrees is the change in temperature. So the amount of enthalpy required would be 10 kilocalories. So that means if I want to represent enthalpy, let's say at 330 Kelvin, enthalpy is this value, and at 340 Kelvin, enthalpy is this value. This difference would be 10 Kelvin, right? I mean, that's how I'm going in terms of our path, if you like, on the enthalpy versus temperature graph. You might have seen some graphs like enthalpy temperature in your 12th standard, 11th standard. Anybody has seen, anybody has plotted these kinds of graphs?
Yes, sir. Temperature versus time graph I have seen.
Temperature versus time. Okay,
Yes.
we are not plotting time now. We are plotting enthalpy. We are not worried about how long it takes to raise the temperature from 330 to 340 Kelvin. We are just worried about the total enthalpy. Okay, shall we go forward?
So, like,
Yeah.
what is the difference between enthalpy and energy?
Yeah. So
Or heat?
so we have used these terms interchangeably: energy, enthalpy, heat. Right? We have used these terms interchangeably, and so energy could be one form of energy is enthalpy, right? You could have a kinetic energy, you could have potential energy, you could have enthalpy being one form of energy, you could have internal energy in the form of rotation, in terms of vibration of the molecule, in terms of translation of the molecule, kinetic energy. So energy is a more broader term. Okay, in this course we are only going to work with one form of energy, or maybe 2-3 forms of energy. In the next course, of course, we will work with more forms of energy, but we are going to work in terms of only enthalpy for this particular course. and heat and enthalpy. Heat, sometimes we use the word heat to say that amount of heat required to change the temperature from 330 Kelvin to 340 Kelvin. What we actually mean is how much enthalpy is required to be supplied to change the temperature from 330 Kelvin to 340 Kelvin. So enthalpy and heat are are one and the same for this course. Right.
Okay, sir.
So when we start doing thermodynamics in the next semester, you might have to distinguish between different forms of energy, and you might have to distinguish between internal energy and enthalpy. Let's not get into that just now. When we talk about energy, you will come across other energy terms as well, like Gibbs free energy or Helmholtz free energy. So free energy is one more concept that will come as we go along, but we will worry about only enthalpy here. All right, can we go forward?
Yes, sir.
Okay, now suppose I say, suppose we say we have a bottle, right, drinking water, and water is in that bottle, and suppose I say I want you to tell me how much mass of water is there in the bottle. How would you tell me? Suppose this bottle is at room temperature, 30 degrees centigrade. Can you tell me what is the mass of water in the bottle? How do you find that out?
So find the volume of the bottle
Yes,
and
Okay.
use the density
Okay,
at
so
30
one
degrees Celsius.
is find volume and then use density. Okay, that's one.
So by measuring the force gravity applies, like weighing it,
Yeah, so
basically.
I'll just take a weighing scale, right? Dot, dot, dot. So many digits are there. I will take the bottle with water in it. I will weigh the contents. So let's say the contents are 308 grams. I will pour out all the water. I will weigh the empty bottle. So let's say the weight is 7 grams. So then therefore this difference must have come from the mass of water in the bottle, right? So that means mass is something that we can measure, right? Either we measure through volume and density, or we can actually directly weigh and make a measurement of the mass, right? And if I know the substance that it is water, I can divide by molecular weight and I can get gram moles of water as well. So 301 grams of water, I divide by 18, that corresponds to 301 divided by 18, whatever is that number, so many gram moles of water. So if I write mass in terms of grams or kilograms or gram moles or kilomoles, I can actually measure, right? Or volume, I can actually measure, right? And because we can measure, and we have been writing balances for, suppose I want to take this as a control volume. If I take this as a control volume and I add water into this bottle, then I can write a balance that water present initially plus water added must be equal to water at the end, or after addition is complete, right? So yeah, I would say that initially I had 301 grams, I added 45 grams of water. That also we can measure, right? This also we can measure, and then we will say that we ended up with 346 grams, right? So these are the kind of balances that we have been writing. Mass coming in, mass added is equal to the mass going out, Now here in terms of there is no in and out. It is just what was initially there and what we added and what we ended up with. Right? But the point is that all these can be measured.
For energy, we can't measure the initial condition as such.
Okay. So I'm just coming to that. Right? Do we all agree? Now suppose I tell you that I have the same bottle, right? Same bottle, same water, same temperature. Can you tell me how much enthalpy is there? Do you agree? Can you tell me? Can anybody tell me? I asked you how much mass of water is there in the bottle and you could tell me. Now I'm asking you how much enthalpy is there in the bottle. Can somebody tell me? Just unmute yourself and say something. Don't just listen.
No,
Just
sir,
answer
we
to
can't.
yourself.
We can't
Okay,
say.
that's one answer. We can't say. That is one answer. Anybody else would like to say? Just say something. If you just remain quiet, nothing is
Yes,
going
sir,
to
we
be
can't
achieved.
say.
Pardon, Amrapali?
We can't say.
We can't say. Okay.
Sir, we can measure only the change in enthalpy, but not only in enthalpy.
So you are saying no, we can't say. And we can only measure. Praveen, is that what you said? What did
Sir,
you
we
say?
can measure the change in enthalpy.
What were the exact words that you said?
Sir, we
I'm
can
writing the
measure
exact
the
words. We can measure.
the change in enthalpy.
We can measure the change in enthalpy.
But not the
Those are your exact words, right?
yes, sir.
How many people agree with that?
Yes, sir, I agree with that.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, fine. What is the verb here? This is not an English class, but if you were to think in terms of English language, what is the verb here?
Measuring.
Measure.
Measure is the verb, right? That means something I am doing and I am measuring. Can I measure enthalpy?
No.
Sir, we can measure enthalpy
So,
in terms of temperature.
Wait. Right? See here, if I take the bottle, I keep the bottle on the weighing scale. And now while on the weighing scale, I add 45 grams of water. Then the weighing scale would change from 308 because water plus the empty bottle, 308 plus 45, the weighing scale will now read 353. I have measured the change. It has changed from 308 to 353. Therefore, I am inferring that I must have added 45 grams of water. 353 minus 308. Can we have a device? Do we have a measuring instrument for enthalpy that I will measure? I will keep this bottle in that instrument and I will raise the temperature from 330 from 30 degrees centigrade to 40 degrees centigrade, and that measuring instrument will tell me I have added, let's say, 1 kg of water, I have added 10 kilocalories of enthalpy. So we do not have a measuring instrument for enthalpy. Enthalpy is a conceptual property. we can infer, oops, we can infer something about enthalpy. How we can infer? We can infer something about enthalpy by measuring temperature. So I can stick a thermometer inside this bottle. I can measure the thermometer, and that or I can see the reading on the thermometer. The thermometer reading will say 30 degrees centigrade. So I am making a statement that this whole water is at 30 degrees centigrade. Now if I heat this water on a burner and I keep on measuring, I say that the temperature is now 40 degrees centigrade. I'm measuring temperature. From that measurement of temperature, from 30 degrees centigrade to 40 degrees centigrade, I am inferring that the amount of heat supplied or amount of enthalpy supplied must be equal to mass into specific heat into change of temperature. So if it is 1 kg into specific heat is 1 kilocalorie per kg Kelvin into 10 degrees centigrade, so 10 Kelvin change, the amount of enthalpy supplied or the amount of heat supplied must be 10 kilocalories. I'm inferring, I'm calculating, I'm estimating
So,
from
but
from the measurement that I have done. The measurement that I have done is temperature. Yeah, Arya, go ahead.
so but this problem is because we don't know what will be the enthalpy at 0 Kelvin, and because of that, and achieving 0 Kelvin is nearly impossible, and that's why we are facing this problem.
Okay, let me let me let me tell you something else. Let's talk about another form of energy. Okay, I have understood your question. We will discuss in due course of time. Let's talk about another form of energy. All right. Okay, which other form of energy shall we talk? Yeah. Okay. Let's talk about potential energy. Right. So imagine there is a room. Imagine there is a room, and imagine it's your room. So imagine there is a cupboard. There is a study table. And there is a chair, right? And you are sitting on the chair trying to study MEPC. And there is your pen. Let's say the mass of that pen is 1 kg. Can you tell me potential energy of this pen?
So the mass of the pen into the height of the table into gravitation, acceleration due to gravity.
Okay, potential energy of the pen is mass of the pen m into g into h. So m is 1, g is 9.81, so kgs, meter per second square, and h. So let's say height of this table is 1 meter into 1 meter, right? So kilogram, so this is joules, so 9.81 joules.
Sir, 1 kg of pen is not possible, sir.
क्यों?
1 kg of pen.
अब मेरा लेड पेन है, कुछ प्रॉब्लम है?
Still 1
ऑस्मियम
kg.
का पेन बना दिया. Will do.
अरे लेड का पेन है, गोल्ड का पेन है, तुमको क्या फर्क पड़ता है? Are we discussing about pen or are we discussing about potential energy?
Yes, sir. Potential energy.
So does it matter whether I have 1 kg pen or I have 100 grams of pen or 5 grams of pen? How does it matter? It just makes life simple. Suppose I say 50 grams of pen, so I have 0.05 grams. Who will do the multiplication? Will you do the multiplication, Praveen? And how much time we will spend in just wasting in terms of doing multiplication, whereas what is important is not the pen but the potential energy. Is that okay, Praveen?
Yes, sir.
Now you permit me to have 1 kg pen? Yes or no? Praveen? Can I have a 1 kg pen, Praveen? Yes, no?
Yes, sir.
Thank you.
The network was lost for a minute.
Thank you. No issue. Suppose this pen I keep here now. What is the potential energy? What is the potential energy of the pen? Same, right? 1 into 9.81 into the height of the cupboard, isn't it? So suppose the height of the cupboard is 2 meters. So now it is 1 into 9.81 into 2. So whatever that is, 19.62 or whatever that number is. Right? So many joules. Do you agree? Yes or no?
Yes, sir.
Yes, sir.
Suppose you are on second floor. So there is a first floor below you. And there is a ground floor below that. Right? And this is your ground. Now suppose, Praveen, there is a window here. Oops, I removed the wall only. I don't want to remove the wall. I just want to make a window. Okay, so there is a window. And Praveen takes this pen. Oops, I don't want to remove the cupboard. So Praveen has taken the pen. Praveen has gone to the window. And Praveen has thrown the pen from the ground floor, from the second floor window. Now the pen is on the ground floor. Praveen just got fed up with MEBC class, just takes the pen, throws it out of the window. Now tell me, what is the potential energy of the pen?
Also, with reference to the surface of the earth, it would be 0.
Praveen?
Yes, sir. It would be 0.
0 what?
With the potential energy of pen.
With reference
With reference to the ground level.
mgh, so 1 into 9.81 into 0, so 0 joules. But suppose now Praveen comes and brings it back. Now he says he's got the answer to the MEBC problem. He's happy. He goes downstairs. He brings the pen that was thrown. Now pen is not on the ground level. The pen is on the floor. Now tell me, what is the potential energy of the pen?
Mass of the pen into acceleration due to gravity into height of the 2 floors.
Height of 2 floors. Oh, now you're saying, suppose each floor is 10 meters, not 10 meters, 4 meters in height or 5 meters in height. Total height is 10 meters. So m into g into h. So 1 into 9.81 into 10. So that is 98.1 joules. Now Praveen picks up the pen. and brings it back onto the study table. Now, Praveen, tell me what is the potential energy of the pen?
Sir, M into G into the height of the two floors plus the height of the table.
Oh, so 10 plus 1, 11, right?
Sir,
But,
20 plus 1.
oh, sorry. No, it is 10 floor. 10 meter is the total height of two
So I
floors.
thought first one floor was 10.
Floors are typically 10 feet, 11 feet, 9 feet in height. So it's about, I'm just taking 5 meters just for simplicity. But you see, that's not what Arya answered right at the start. What Arya answered right at the start was 1 into 9.81 into 1. Now you're telling me it is 1 into 9.81 into 11. Pen is at the same place on the table. Initially, Arya told me it is 1 into 9.81 into 1. Everybody agreed. Now you are telling me it is 1 into 9.81 into 11. Obviously, they are not the same.
Sir, it depends on reference point, sir.
It depends on what?
Reference point. Where we take
Reference.
0.
Reference. That means again, energy is not a measurable property. It is a conceptual property. We are inferring about potential energy by measuring height. Do you agree with that? So if I have to measure height, I have to measure height with respect to something. If I'm measuring height with respect to the ground level, then height of the floor is 10 meters. Height of the study table is 11 meters. Height of the cupboard is 12 meters. But if I'm measuring with respect to the floor of this person's house, then pen is at 0 meters, or pen is at 1 meter height, or pen is at 2 meter height. Right? So we are defining height in this particular case with respect to some basis, or as we would like to call, with some reference. And we will say that at this reference height, potential energy is 0. So if the pen was here, we said this is our reference level. We said that potential energy is 0 at this reference level. Now we will bring the pen back to the floor, second floor. The change in potential energy was 1 into 9.81 into the change in height of the pen, 20 meters. So many joules. And therefore we will say the potential energy of the pen at this location was 0 plus how much change was there. Change was 1 into 9.81 into 20, and that's the potential energy of the pen at this particular point. or when you answered initially, you took the reference as here. And at this reference height, you said potential energy is 0. And therefore, you said that the potential energy of the pen is 1 into 9.81 into 1, or the potential energy is 1 into 9.81 into 2. Whereas that was only the change in potential energy required to bring the pen from the reference state to the top of the study table, or from this reference state to the top of the cupboard. What you had told me was the change in potential energy, but you told me absolute value of potential energy because in your mind you had made this floor as a reference. You had made this as a 0 potential energy state. Do you agree with that? Arya, Praveen, do you agree with that?
Yes, sir.
Sir, I had a doubt, sir.
Yes, yes.
Sir, I don't understand the logic behind the term, sir, conceptual property. So shouldn't all energies be a conceptual property? Like, how do we
Yes.
decide if something is not a conceptual property and something is?
Is there a measuring instrument for energy? Is there a
No,
measuring
sir.
instrument for potential energy?
No, sir. So all types of energies should be conceptual properties, right?
Yes, yes,
Right. All right.
yes, yes. So there are several other conceptual properties as well, as you will come across. You might have heard some names. Can you tell me some more conceptual properties that you have you are aware of? Or
Entropy,
maybe
sir.
you have
Entropy.
Absolutely, entropy is a conceptual property. I have no way of measuring entropy. I have no way of measuring. I don't have any instrument to measure entropy. Any other
Not at the moment, sir.
thing?
Work.
Work, yes, yes. Work is a conceptual property.
Heat.
Heat, yes, we talked about heat. Gibbs free energy.
Yes,
Word
sir.
of Gibbs free energy.
Yes, sir.
Right. So that's a conceptual property. I don't have any measurement of Gibbs free energy, but we can infer something about Gibbs free energy or change in Gibbs free energy by measuring some property, by measuring temperature, by measuring pressure. You will see that in your thermo course. What are the things that we need to measure to find out about Gibbs free energy? So there are two important points that we are talking about. One important point that we are talking about is that we can infer something about enthalpy by measuring temperature. Not just temperature, mass as well, right? Because enthalpy is a extensive property. It will depend on mass. If I take 1 kg of water at 30 degrees centigrade, I heat it up to 40 degrees centigrade, enthalpy change would be 10 kilocalories. If I take 2 kgs of water, enthalpy would be 20 kilocalories. Something about temperature, something about mass, provided we know the specific heat. Second thing is we can calculate change of enthalpy by finding out the mass of that substance, finding out the specific heat of that substance, and finding out the change of temperature. Right? And then we can calculate the change of enthalpy. But if I have to put a value on enthalpy, if we put a value on enthalpy, we need to define a reference condition. And we need to say that at this reference condition, enthalpy is 0. So one reference condition could be 0 Kelvin. We will say that at 0 Kelvin, enthalpy is 0, and then we will work out change of enthalpy by taking something from 0 Kelvin to, let's say, 40 Kelvin or 40 degrees centigrade, and then say, this is the change in enthalpy. Therefore, with respect to this reference, the enthalpy of that substance is so many joules, right? Just like the potential energy. We say reference is 0 here, or reference is 0 here. With respect to this reference, we can work out what is the change in potential energy, and then we can assign a value to that potential energy, right? Why are we doing this? Why are we wanting to put a value on enthalpy? Okay, that point may not be quite clear. Rather than worrying about, why not just worry about changes in enthalpy? Why do you want to put a value on enthalpy? Do you understand the difference between change in enthalpy and putting a value on enthalpy? Yes, no?
So like we are measuring change in enthalpy by putting a value also.
No. We are putting a value on enthalpy by making something reference. So if I say that my reference is ground floor, the change in potential energy is 1 into 9.81 into 10 meters. That is the change in potential energy. That is 98.1 joules by taking the pen here, isn't it? By taking the pen here from here. So we are saying that potential energy of the pen is at this location is 98.1 joules. That 98.1 joules is with respect to this reference. We have put a value on potential energy, but that value we have put in by saying that my potential energy is 0 at this location, the reference condition. Do you agree? If I say this is the reference, if I say this is my reference height, potential energy is 0 here. My potential energy of the pen is 0 here. My potential energy of the pen is 1 into 9.81 into 1. It is 9.81 joules here. Potential energy here is 1 into 9.81 into 2, 19.6 joules. We are putting a value. We are putting a value. We are putting a value with respect to either this reference or with respect to this reference. Or you might want to put a reference as center of the earth. Is that okay?
Yes, sir.
It may not be very clear to you just now why we are putting a value on enthalpy. Okay, but here is something that we are going to do. It will become clear as we go along. So we are taking a control volume. So we are saying, let's say substance A is coming in, or let's say oxygen is coming in. We are saying oxygen coming in minus oxygen reacted, or there might be a process in which oxygen is generated. Oxygen generated must be equal to oxygen going out. Right? This is what we have been doing ever since we met. Isn't it? Yes or no?
Yes, sir.
Yes, sir.
Now, suppose I want to talk about energy or enthalpy. And suppose I say hot air comes in at 30 degrees centigrade, or hot air comes in at 60 degrees centigrade. I want to heat that air and I want to get hot air at 180 degrees centigrade. So we would like to write in an analogous manner enthalpy coming in from air at 60 degrees centigrade plus enthalpy added, because we might be supplying heat from a burner. We might be having a burner here and we will supply enthalpy, supply heat, must be equal to enthalpy of air going out at 180 degrees centigrade. So just like we have been writing mass balances, we would be wanting to write energy balances. So for that, we would need to write enthalpy in terms of some kind of value. So we will say enthalpy at 60 degrees centigrade plus enthalpy added. Now suppose I say enthalpy at 60 degrees centigrade is 0. Suppose I say my reference state is 60 degrees centigrade. Air has 0 enthalpy at 60 degrees centigrade. Then we will say, this value is 0 plus whatever we have added. We added suppose 30 joules, or if we know the mass, if we know the specific heat, we can find out the enthalpy at 180 degrees centigrade with respect to this reference condition. And we say, this enthalpy is 50 joules and enthalpy going out is 50 joules. So then we can say, I must have added 50 joules of enthalpy by way of combustion or by way of this burner. So we would need to write enthalpy in terms of absolute units, in terms of some quantity. We might want to put some number on enthalpy. Okay? Don't worry if this is not clear to you, it doesn't matter. We will start doing problems and then all these things would be fairly straightforward. Okay? Let's take some examples. All right. Do you want a break of 5 minutes?
Yes, sir.
Okay. Let's have
Yes,
a break
sir.
let's have a break of 5 minutes. It's 9:25. So we will assemble at 9:30. Okay, let's start. So suppose we were plotting graphs of enthalpy versus temperature, right? So enthalpy versus temperature graph we were plotting. So what is the origin? Should we take this origin as 0 Kelvin and 0 enthalpy? That can be one way of saying, taking this as a plotting this graph. But suppose our temperature change is only from 330 Kelvin to 360 Kelvin, we would have to plot this graph right from 0 Kelvin, right? So that's not a good idea. Why not we plot this graph straight away from 300 Kelvin? Or why not we plot this graph x-axis only from 330 Kelvin, right? And maybe 340 is here, 350 is here, 360 is here. Okay. So now the start point of our graph, the origin of our graph is on the x-axis, it is 330 Kelvin. Same way, I can say that enthalpy of some substance, I can say at 330 Kelvin is my reference temperature or reference condition. And at this reference condition, I will say enthalpy is 5000 joules. It is reference, right? I can say whatever value I want at the reference. So then my graph would be 330 Kelvin and the y-axis will start from 5000. Or I will say that at this reference condition, enthalpy of some substance, enthalpy of air, let's say, is 400 joules. So then my graph will start from 400 joules. Or I can say that at 330 Kelvin, my reference condition enthalpy is 0 joules. I will start from 0. So suppose I take 1 kg of air and I want to heat from 330 Kelvin to 360 Kelvin. Let's make it 330 to 360 Kelvin, and let's say Cp of air is 0.24 kilocalories per kg Kelvin. So then the change in enthalpy would be 1 into 0.24 into 360 minus 330. So that is 30 Kelvin. So this would be 7.2 joule. Oh, sorry, 7.2, not joules, 7.2. Sorry, 7.2 kilocalories. Specific heat as units of kilocalories. Okay. So if I say enthalpy of air at 330 Kelvin is 0 joules, enthalpy at 360 Kelvin, this number would be 7.2 kilocalories or 0 kilocalories. But if I say that my reference condition enthalpy is 100 kilocalories, then this would be 100 and this would be 107.2. If I say that at 330 Kelvin, my reference condition enthalpy is 1000 kilocalories, then this would be 1000 kilocalories, and at this condition it would be 1007.2 kilocalories. Do you agree with this? So the change in going from 330 to 360, that change is 7.2 calories. Whatever we call our reference, correspondingly we will plot a graph. Just a way of saying where does my y-axis start. If my y-axis starts at 0, it is 7.2. Do you agree with this? Yes, no?
Yes, sir.
Okay.
Yes, sir.
So if I'm plotting this graph in terms of enthalpy per unit mass, right? I have taken basis as 1 kg. I mean, I have taken 1 kg of air. So rather than plotting enthalpy, I can plot in terms of enthalpy per unit mass versus temperature in Kelvin. Right? So if I take 10 kgs of air, then enthalpy change would be 1 into 10. Oops, instead of 1, it is 10 into 0.24 into 30. It would become 72 kilocalories, isn't it? But if I'm plotting in terms of enthalpy per unit mass, because why I won't like to plot in terms of mass is because I can just straight away do the calculation for 1 kg and I just multiply by the total amount of or total mass of the air that I have. And then we call this as specific enthalpy per unit mass. So then specific enthalpy becomes an intensive property, whereas enthalpy would become an extensive property. Does everybody understand what I mean by intensive and extensive?
Yes, sir.
Are you hearing these words for the first time? Intensive and extensive, or you have mugged them
No,
up?
sir, we have heard in
You have
12th.
mugged them up in your 11th standard, or 10th standard, or 8th standard, and you've written a short note on enthalpy.
Yes, sir.
Right? So is that clear? A specific enthalpy is now independent of mass, right? It is per unit mass. So it becomes an intensive property, whereas actual enthalpy, it becomes an extensive property because it will depend whether I have 1 kg of mass or 2 kg of mass or 10 kg of mass. Is that okay?
Yes, sir. Yes, sir.
Okay. Can you tell me what is the slope of this graph? What is the value of slope?
Point 24.
0.24, or should we say something else?
Specific heat of air.
Yeah. Right. So that means if I write specific enthalpy versus temperature, if I have a change in temperature dT and change of specific enthalpy is, say, dE, if you like, then dE by dt, this is dE by dt is how do you relate dE and dt?
M into Cp.
Now I'm saying that E is specific enthalpy, or if you like, okay, so you might say E, you want it to be enthalpy, and let's say E bar, suppose you want it to be specific enthalpy. Enthalpy in terms of kilocalories, oops. Specific enthalpy in terms of kilocalories per kg. So now if you say dE bar, what is that dE bar? How do you relate it to dt?
Cp
Cp/dt, right? Or dE bar by dt, what would that be?
Cp.
Cp, right? So that's the meaning of specific heat. For 1 kg of the material, what is the change in enthalpy, or in terms of specific enthalpy, what is the change in specific enthalpy for a 1 Kelvin change in temperature, right? Now suppose for some substance I say that specific enthalpy versus temperature is like this. What does it tell you about this substance?
Specific enthalpy is not linearly dependent on the temperature.
Okay. What does it tell us in terms of CP?
CP is dependent on temperature.
Yeah,
It
so
decreases with
CP is
temperature.
different here. CP is the slope of this graph here. CP is the slope of this graph here. CP is the slope of this graph here. CP at this temperature is the slope of this graph here. All right. So we can say that specific heat is not a constant number. It depends on temperature. Okay. So CP is some value here, slope. So let's say this is 330, this is 400, this is 500, this is 800 Kelvin. Temperature in terms of Kelvin. So CP at 330 Kelvin is this value, the slope here. CP at 400 Kelvin is the slope here. CP at 500 Kelvin is the slope here. CP at 800 Kelvin is the slope here. So CP is a function of temperature. Do you agree with that? Don't worry about whether the temperature relationship is like this, or it is like this, or it is like this. Some kind of temperature relationship I have. Yes, Praveen.
Sir, the phase didn't change, right?
Yeah, assuming that there is no change of phase. Okay.
Yes, sir.
So now, suppose I say that Cp is some function of temperature. Suppose that function of temperature is like this. Well, I will. So can you tell me how much enthalpy would be required to heat up something from 330 Kelvin to 800 Kelvin? So suppose this is air. I want to heat up air from 330 Kelvin to 800 Kelvin. What would be the, how would I calculate the change in enthalpy of air from 330 Kelvin to 800 Kelvin? Or I will say change in specific enthalpy, which means I'm taking 1 kilogram of air. How will I calculate? Suppose I say that Cp here is 0.24, Cp here is 0.23, Cp here is 0.21, Cp here is 0.18. How will you calculate the enthalpy required, or change in enthalpy, change in specific enthalpy of air? How much in from 330 Kelvin to 800 Kelvin? How will I calculate that? If Cp is a function of temperature.
So we integration.
Right. So I will take small intervals of temperature So from 330 Kelvin, I will take 1 Kelvin change, 330 to 331, 331 to 332, 332 to 333, 333 to 334. Like this, I will take intervals of 1 Kelvin right from 330 Kelvin to 800 Kelvin. Now, for this small interval of 330 to 331, I will say that Cp is constant and constant equal to 0.24. Over the change dt, over this 1 Kelvin change from 330 to 331, I will say Cp value is 0.24. Then I will take an interval from 331 to 332, and I will say over this interval Cp is, let's say, 0.239. So if I have to go from 330 to 800, I will have to add up all such intervals from 330 to 331, 331 to 332, 332 to 333, and so on. Do you agree with that?
Yes, sir.
And this is nothing but the area of that trapezoid. This is nothing but area of the next trapezoid. And this is nothing but the area of the next trapezoid. And the next trapezoid, and the next trapezoid, and the next trapezoid, and the next trapezoid. We have just done trapezoidal rule for adding up areas of trapezoids. What have we done? Right? Have we not integrated Cp from 330 Kelvin to 800 Kelvin? Do you agree with that? Yes, no?
Yes, sir.
Yes, sir.
Right? All we have said is dE bar is Cp dt, and we have just, or rather than saying dE bar by dt, we have approximated this by trapezoids, delta E bar by delta T, and this is equal to Cp. So delta E bar is Cp delta T, and we have just added up all these delta T's. So total enthalpy change, or total change of specific enthalpy, would be just Cp1 delta T1, Cp2 second trapezoid delta T2, third trapezoid delta T3, fourth trapezoid, and so on. Right? Is it not the same as Cp dt from 330 to 380? Do you agree? Yes, no?
Yes.
All right, do you agree? Can we go forward?
Yes, sir.
So I'm going to give you this function for some cases, for some gases, for some substances. So let's say the Cp as a function of temperature, this function is like this: A plus Bt plus Ct square. Cp is in terms of calories per gram mole Kelvin, And in this relationship, temperature is in Kelvin. Right? I'm going to tell you the values of A, B, and C. These are the constants. So I'm going to tell you for nitrogen and oxygen. The value A is 6.457. B multiplied by 10 raised to 3 is 1.389. C multiplied by 10 raised to 6 is minus 0.069. Oxygen, the value is 6.117, 3.167, and minus 1.005. Okay, somebody has to do experiments and find out these values, right? So,
Sir, shouldn't
just
it be
yeah.
10 power minus 3 and 10 power minus 6?
Yeah, so we are just coming to that. Okay. Suppose I want to find Cp of nitrogen at 500 Kelvin. Okay. So what would be that value? Cp from this relationship. Cp would be A. A is 6.457 plus, now B multiplied by 10 raised to 3 is equal to 1.389. So B would be 1.389 multiplied by 10 raised to minus 3. Okay. B multiplied by 10 raised to 3 is this number. C multiplied by 10 raised to 6 is this number. Is that okay, Arya?
Yeah, understood.
So C into 10 raised to 6 is minus 0.069. So C is equal to minus 0.069 into 10 raised to minus 6. Okay, now what is the B value? It is 1.389 into 10 raised to minus 3 multiplied by temperature. Temperature we want is at 500 Kelvin plus C. Now C is minus 0.069 into 10 raised to minus 6 multiplied by temperature square. So that is 500 square. So can you tell me what is the Cp of nitrogen at 500 Kelvin? Somebody calculate and tell me.
Seven point 13425.
So Cp of nitrogen at 500 Kelvin is 7.134 calories per gram mole Kelvin. Right? Find the Cp of oxygen at 800 Kelvin. Cp at 800 Kelvin would be A 6.117 plus B, it is 3.167 into 10 raised to minus 3 into 800 minus plus C. Now C is minus 1.005 into 10 raised to minus 6 into 800 square. So Cp would be somebody tell me the value.
So 8.007.
At 8.007 calories per gram mole Kelvin. Any doubt, any difficulties? Any issues? Anything you want me to repeat? Everybody gets these values?
Yes, sir.
Yes, sir.
Okay. Okay, here is the next problem. Suppose in some plant, we want to heat up air from 30 degrees centigrade to 600 degrees centigrade. And suppose we want to heat up air. Suppose we want to heat up 100 gram moles of air from 30 degrees centigrade to 600 degrees centigrade. What is the enthalpy change for air? Can you tell me? Can you calculate? What is the enthalpy change of air when air is heated from 30 degrees centigrade to 600 degrees centigrade and we have 100 gram moles of air? Can you calculate?
Yes, sir.
Once you have some answers, you can tell me.
Sir, I am getting 7.91 into 10 power 5.
What? Units?
The given units, calories,
Not given units. You tell me whatever are your units.
calories.
7.91 into 10 raised to 5 calories. Right? So shall we just say 791 kilocalories?
Yes, sir.
Who was getting 791? Dharmik, was that you?
Sir, me, Ansh.
Ansh. I still don't recognize your voices. So horrible to not be meeting and seeing you. Okay, any other answer? Ansh, will you volunteer and show us the solution?
Yeah, sure, sir.
Okay, great. We'll just wait for some more time, then you can explain how you got 791. I don't know whether it is right or wrong. By the way, we are just assuming that this is dry air. So I have not told you relative humidity and all those things. So we are assuming that this is dry air. And dry air is 79.21 mole percent nitrogen and oxygen.
Sir, I am getting a different answer.
Okay, what is your answer?
417.5 kilocalories.
417.5. Okay, so shall we just say 418 kilocalories?
Yes, sir.
Sir, I realized the mistake. I didn't consider the mole percent. So I'll change the answer. I'll calculate.
Oh, okay.
Yeah, I'll confirm in a minute.
Okay. 418 is one answer. Any other answer? Any other answer? Ansh, have you revised your answer yet, or you're calculating?
Yeah, I'm checking it once again.
Oh, okay.
So I got same as Praveen's answer.
Okay, so 418.
Yes, sir, me too.
So 418, sir.
Many people are getting 418.
Same, sir. 418.
We'll just wait for Ansh to finish. Om, any answer?
Sir, I am calculating.
Okay. Why does it take so long?
Sir, I got 416.3 kilometers.
Amol, you are saying how much? 41?
416.3.
Okay, 416.3, 418. They are same.
Sir, even I got 418.
Okay.
So I also got 418.
Okay. Ansh, would you like to tell us how you got now?
Yeah, I'll start. I'll recognize the mistake somewhere else. Then.
Yeah, while you can
Yeah.
tell us, and there you will spot your mistake.
Yeah. Actually, I integrated the CP equation with dt.
Okay, so shall we say that enthalpy change for air would be equal to enthalpy change for nitrogen plus enthalpy change for oxygen. Can we make that statement?
Yes.
So now enthalpy change for nitrogen, if I am taking 100 gram moles, I will have 79 gram moles of nitrogen and 21 gram moles of oxygen. Right, so enthalpy change for nitrogen would be 21 multiplied by Cp. Now Cp just happens to be a function of temperature, so we'll just have to
So
integrate.
79 into.
Oh, sorry. Yeah. Correct. Nitrogen. So 79 into Cp into the change of temperature, and we'll just have to integrate from 30 degrees centigrade. So 30 degrees centigrade, we are converting it to Kelvin. So that would be 303 Kelvin, and 600 degrees centigrade would become 873 Kelvin, right? Why? Because this Cp is given as a function of temperature, and the units of temperature for this particular relationship are Kelvin. Do you agree with that,
Yes,
Ansh?
sir. Yes, sir.
Right. So we will have to integrate from 303 Kelvin to 873 Kelvin. And Cp enthalpy change for oxygen would be 21 multiplied by Cp dt. Again, this is to be integrated from 303 to 873. And this particular Cp is for nitrogen, and this particular Cp is for oxygen. They are different, right? So if I put in these values now, it would be 79 multiplied by integration of 303 to 873. 6 A, B, and C are given. So A, B, and C is 6.457 plus B is 1.389 into 10 raised to minus 3T plus C, and C happens to be minus 0.069 into 10 raised to minus 6T square. This whole expression is to be integrated with respect to temperature, right? Plus 21 multiplied by integration of Cp from 303 to 873, and the Cp expression for oxygen is 6.117, that is A, plus B is 3.167 into 10 raised to minus 3T plus C, and C happens to be minus 1.005 into 10 raised to minus 6T square. This whole expression is to be integrated with temperature from 303 to 873. Ansh, is that okay?
Yes, sir.
Right. So we can expand 79 multiplied by 6.457 integral with respect to temperature. That would just be 873 minus 303 plus now integration of T. So that is T square by 2, 1.389 into 10 raised to minus 3 divided by 2 T square, 873 square minus 303 square minus T square integrated. So that is 0.069 into 10 raised to minus 6. Integration is T cube by 3. 873 cube minus 303 cube. Okay. That is for nitrogen, plus oxygen now 21 multiplied by the next integration 6.117, 873 minus 303 plus 3.167 into 10 raised to minus 3 divided by 2, 873 square minus 303 square minus 1.005 into 10 raised to minus 6 divided by 3 T cube. So 873 cube minus 303 cube. And then if you simplify, you will get whatever value in terms of calories, because Cp is given the units of this expression. Cp is in terms of calories per gram mole Kelvin, and you can divide by 1000 if your number is very large, and you can convert it into kilocalories. Ansh, is that okay? Is that what you have done?
Yeah. Then I calculated for the numbers.
Yeah, so maybe just some calculation mistake has happened.
Yeah, I got my
Sir,
mistake.
what-
I'm getting 417.4.
Okay, fine. Yeah, somebody was asking some doubt.
Sir, what I did was I calculated first the ABC value separately for air by using their mole composition, and then calculated the integral.
You calculated ABC values for
Air first.
air.
Separately.
Okay, fine. What you are doing is actually from here you are taking out 873 minus 303 common. here you are taking out 873 minus 303 square divided by 2 common, and here you are taking 873 cube minus 303 cube divided by 3, you are taking that as common. So what you are saying is 79 into 6.457 plus 21 into 6.117 into 873 minus 303, or you are taking out 100 also common. You are saying this is 100 multiplied by 0.79 multiplied and 0.21 addition, and then you are taking out 100, you have taken out way common, and then you are taking 0.79 into 1.389 into 10 raised to minus 3 plus 0.21 into 3.167 into 10 raised to minus 3. This multiplied by 873 square minus 303 square divided by 2, and so on. Do you agree with that?
Yes, sir.
Right, that's what you've done, right?
Yes, sir.
So either you say that for 1 gram mole air I will do and then multiply by 100, or you do this way, one and the same thing, you are going to get the same answer. Is that okay?
Yes, sir.
All right. If you have a calculator, 991 ES plus, look on your calculator, there is an integration symbol. Do you have a calculator which has an integration symbol?
Yes, sir.
There will be an integration symbol, and you can do the integration on the calculator itself. So you don't have to keep on doing this on a calculator. You can simply type this expression on the calculator and it will tell you the integral value. You can simply type this integration on the calculator and it will tell you the integral value. Right? How many people have this kind of calculator with an integration value symbol where you can do integration? Even if you have the older calculator, where is that older calculator gone? 991 MS or something like that. 1 second, let me get that old calculator. Some of these old calculators, if you have FX82 MS, it won't have the integration, but there are some other versions of 991 ES Plus that will have the integration inbuilt function, right? So look at your calculator. If your calculator has an integral function, straight away you can use it for integration. It will make your life so much simpler. Okay, shall we go forward? One last point and then we will stop. Okay, shall we go forward? Any other doubt? Shall we go forward? Is there any doubt?
Yes, sir.
All right. So suppose, next problem. Imagine that we have, let's say 5 kgs of water in the liquid state, and we want to heat up this water. We have 5 kgs of liquid water at 30 degrees centigrade. We want to heat this up and make it 5 kgs of water vapor. We want to make it into 5 kgs of water vapor at 120 degrees centigrade. Okay. Can you tell me what is the enthalpy change for water, or enthalpy change for this operation? Okay. You can assume that Cp is constant. For liquid water, oh sorry, sorry. Cp is 1 kilocalories per kg Kelvin for liquid water, and Cp is 0.45 kilocalories per kg Kelvin for water vapor. And you can assume that these are independent of temperature. Assume they are constants. They don't change with temperature, whether it is 30 degrees centigrade or 31 degrees centigrade or 45 degrees centigrade or 68 degrees centigrade. Cp remains 1 for liquid water. And
Sir,
Cp
we would also
remains
require the
at
latent heat.
0.45 kilocalories per kg Kelvin for water vapor. Can
Yes,
you
sir. There is
calculate-
phase change.
Can you calculate the enthalpy change for this operation?
Sir, we would also require the latent heat.
Latent heat.
Yeah, okay. So you want latent heat. All right, let me give you latent heat. Can you Google latent heat? Ask Google.
So 2260.
Okay, so you are telling me the enthalpy change.
No, sir. So I'm telling latent heat of vaporization.
Oh, don't tell me latent heat. Let everybody Google for themselves. People are so comfortable with Google that people like to Google the answer themselves or values themselves. One reason for asking you to Google is that Google will tell you in different set of units, and therefore you will be forced to convert one set of unit into another set of unit. Nowadays you can actually ask Google rather than type in Google. Isn't it? Do people ask Google or you don't ask Google?
Sir, I am getting answer 3095 kilocalories.
Yes, sir, same.
So enthalpy change. Okay, let me write answer and frequency. Yeah, Praveen, what is your answer?
3095 kilocalories.
3095 kilocalories. Okay.
Sir, I got 2700 kilocalories.
2700 kilocalories.
So
Sir, I got same as
3095.
Praveen.
3095, sir. So 3095.
3 answers for
3095.
4. Who got this 2700?
Sir, I Rishikesh Narwade.
Yeah, Rishikesh.
Sir, he only calculated the latent heat energy.
I don't know. I don't know whether 3095 is right or 2700 is right.
Sir, I'm getting 3095 kilocalorie.
Okay, Smith.
Sir, even I'm getting 3095.
Okay. Anybody else?
Sir, 30.
Anybody else?
$3095.
Ansh. Now I could recognize your voice.
Yes, sir.
Anybody else? Okay. Shall we stop for the day? You can look at all these basic concepts. You can revise this lecture.
Sir,
Yeah.
I put 3095. Sorry, it was wrong. Calculation error.
Rishikesh. So you want to change from 2700. Okay. Shall we stop?
Okay, sir.
Yeah. So please revise this lecture. Rishikesh is removed his answer. So please, I will share the recording. Please go through this lecture, revise these concepts. So from Thursday onwards, we can go to more real life problems. These are just some basic problems I'm taking just to clarify the concepts and just to get you to do some calculations. And so from Thursday onwards, we will start doing more calculations about the process, different kinds of processes and different things. Okay. So let me stop sharing and let me stop recording. Okay, so have fun.